Section: Introduction. In this section, we explore whether deep learning models can be trained to identify data structures from the ground up. Our inquiry is driven by two main motivations. First, from a scientific perspective, deep learning models are increasingly capable of performing tasks that were once thought to be exclusive to humans, such as image recognition and natural language processing. Designing data structures and algorithms is particularly complex, as it involves navigating a vast and intricate space. We are curious about what it would take for these models to tackle such challenges. There are already encouraging examples where models have discovered efficient algorithms for matrix multiplication, solved SAT problems, and developed optimization techniques for various tasks. Our focus here is on discovering data structures, specifically for nearest neighbor search. Second, we have practical motivations. Data structures are essential for efficient querying, but traditional designs often aim for worst-case performance, ignoring the specific patterns in data and queries that could lead to more efficient structures. Recent efforts have explored learning augmented data structures that adapt based on data distribution, but these still rely on expert knowledge for their design. We aim to take a step further by allowing deep learning models to autonomously discover both data structures and query algorithms in an integrated manner. We break down data structure problems into two main steps: constructing the data structure and executing queries. The first step involves transforming a raw dataset into a structured format, while the second step retrieves answers to queries from this structure. We evaluate the performance of data structures based on space complexity, which measures memory usage, and query complexity, which counts the number of lookups needed to answer a query. Typically, we can balance these two aspects against each other. To facilitate learning these structures, we employ a data processing network that maps raw data to a structured format and a query network that learns how to use this structure for queries. We impose constraints on the size of the data structures and the number of lookups allowed, ensuring that both networks are trained together in an end-to-end manner. This joint training helps the data structure and query algorithm to be optimized for each other, and it encourages the learning of lower-dimensional representations that capture relevant features of the data. We apply this framework to nearest neighbor search in both low and high dimensions, as it is a well-studied problem with practical significance. We also investigate frequency estimation in streaming data and consider other potential applications of our approach. In one-dimensional nearest neighbor search, our data processing network learns to sort the data while the query network learns to search through the sorted data. When the data follows certain distributions, the query network can outperform traditional binary search. In more complex scenarios, it adapts by discovering binary search, which is optimal for worst-case situations. Notably, our model learns that sorting followed by the right search algorithm is effective for one-dimensional nearest neighbor search without needing explicit guidance. In two dimensions, when the data is uniformly distributed, our model discovers a data structure that surpasses the performance of KD trees. In more challenging distributions, the learned structure resembles a KD tree, which is interesting since KD trees are complex structures built by recursively partitioning data and finding medians across dimensions. Section Summary. In this section, we explore the potential of deep learning models to autonomously discover data structures and query algorithms, particularly focusing on nearest neighbor search. We propose a framework that involves a data processing network for constructing data structures and a query network for executing queries, demonstrating that end-to-end training can lead to efficient solutions that adapt to various data distributions. Section: Useful Representations in High Dimensions, Section 2.4. In this section, we discuss useful representations in high dimensions. For high-dimensional data, our model learns representations that enhance the efficiency of nearest neighbor searches. For instance, when working with data from a uniform distribution on a 30-dimensional hypersphere, we partition the space by projecting onto two vectors, akin to locality-sensitive hashing. When we train on an extended 3-digit MNIST dataset, the model identifies features that reflect the relative ordering of the digits, sorts the images based on these features, and conducts a search on the sorted images, all learned together from the beginning. Next, we address the trade-off between space and query efficiency. An ideal data structure can utilize extra space to boost query efficiency by storing additional statistics. Our learned model shows that performance consistently improves as we allocate more space, both in low and high dimensions. This indicates that the model effectively balances space and query efficiency. We also explore the classical problem of frequency estimation, where a model with limited memory observes a stream of items and must estimate the frequency of a specific item. Our learned structure takes advantage of the underlying data distribution, outperforming traditional methods like count-min-sketch, showcasing the framework's broader applicability beyond just nearest neighbor searches. In terms of nearest neighbor search, we define our dataset as a collection of points, and the nearest neighbor of a query is the point that has the smallest distance to it. We primarily focus on the case where this distance is the Euclidean distance. Our goal is to create a data structure that allows us to find an approximate nearest neighbor using a limited number of lookups. When the number of lookups is equal to or greater than the number of points, we can easily find the nearest neighbor through a linear search. However, we are particularly interested in situations where the number of lookups is much smaller than the number of points. We set up a data processing network to transform a raw dataset into a usable data structure. Our network is based on an 8-layer transformer model. For nearest neighbor searches, we want the data structure to maintain the original inputs while reordering them, as the answer should be one of the dataset elements. The model achieves this by assigning a rank to each element, which is then used to reorder them. Specifically, the transformer takes the dataset as input and outputs a rank for each point. These rankings are sorted using a differentiable sorting function, resulting in a permutation matrix that indicates the order based on the rankings. By applying this matrix to the dataset, we obtain a reordered version. This ranking approach allows the transformer to avoid needing to reproduce the exact inputs. We also consider cases where the data structure can use extra space. To accommodate this, the transformer outputs additional vectors that can be accessed by the query execution network. We create the data structure by combining the reordered inputs with these extra vectors. The query execution network's role is to find an approximate nearest neighbor for a given query using a set number of lookups. This network consists of multiple query models, each producing a one-hot vector that indicates a lookup position in the data structure. To perform the lookup, we calculate the value at the specified position in the data structure. Each query model also considers the query execution history to inform its decisions. The final output for the nearest neighbor query is derived from the last lookup vector. To ensure we only perform the specified number of lookups, we require each lookup vector to be one-hot. However, this constraint complicates training since it is a non-differentiable operation. Instead, we use soft lookups during training, where the output is a softmax function that sums to 1. To encourage sparser queries, we introduce noise to the logits before applying the softmax, which helps the network learn to produce more robust outputs. During inference, we do not add noise and ensure the lookup vector is one-hot by applying a hardmax function to the output. Section Summary. In this section, we describe how our model learns efficient representations for high-dimensional data, enabling effective nearest neighbor search and frequency estimation by leveraging a transformer architecture to rank and reorder data. We also detail our query execution network, which outputs approximate nearest neighbors through a budgeted number of lookups, utilizing techniques to ensure sparse and robust query selections during training and inference. Section: Data Generation and Training. In this section, we describe our process for generating data and training our model. Each training example consists of a dataset, a query, and the nearest neighbor. We start by sampling a dataset from a specific distribution, then we sample a query from another distribution. Next, we find the nearest neighbor by calculating the distance between the query and each data point, using the Euclidean distance unless stated otherwise. The distributions for the dataset and query vary depending on the specific scenario we are examining. Once we have a training example, our data processing network transforms the dataset into a structured format. Then, the query execution network uses the query to retrieve the nearest neighbor from this structure, producing an output. We apply stochastic gradient descent to minimize the difference between the actual nearest neighbor and our model's output, using either squared loss or cross-entropy loss, depending on which performs better in a given setting. We train our models for up to 4 million gradient steps, using a batch size of 1024, and we implement early stopping. After training, we evaluate our model on a set of 10,000 inputs generated in the same way. For evaluation, we focus on our end-to-end model, which we call E2E, across one-dimensional, two-dimensional, and high-dimensional nearest neighbor problems. We mainly examine data structures that do not require extra space, but we also consider cases where additional space is used. We compare our model against appropriate nearest neighbor data structures and various ablations to understand the impact of different components. In our uniform distribution setting, both the data and query distributions are uniform over the range from -1 to 1, with 100 data points and 7 query models. We track the accuracy of identifying the nearest neighbor after each lookup. We find that our trained model learns to sort the data effectively, achieving about 99.5% accuracy in positioning inputs correctly, even without explicit sorting feedback during training. Additionally, our model develops a search algorithm that surpasses binary search by leveraging knowledge of the data distribution, allowing it to start searches closer to the nearest neighbor. For example, if the query is close to 1, the model begins its search near the end of the list. The small sorting error we observe likely contributes to slightly reduced performance on the final query. To assess the importance of different model components, we compare against various ablations. The frozen model, which does not train the transformer, only positions about 9% of inputs correctly, highlighting the necessity for the transformer to learn effective ranking. The non-adaptive model, which lacks access to query history, also underperforms, as it cannot adapt to the needs of one-dimensional nearest neighbor search. The no-permute model does not retain inputs well enough for accuracy measurement. Overall, these comparisons emphasize the importance of learned orderings and query adaptivity in our model's performance. Section Summary. In this section, we describe our data generation and training process, where each training example consists of a dataset, a query, and its nearest neighbor, with the model learning to sort and search effectively through end-to-end training. We evaluate our model's performance against various baselines and ablations, demonstrating that learned orderings and query adaptivity are essential for achieving high accuracy in nearest neighbor search. Section: Zipfian distribution. In this section, we explore the Zipfian distribution, which has been shown in previous research to reflect real-world query patterns where a few items are searched much more often than others. We set up our experiment with a uniform distribution over the numbers 1 to 200 and a Zipfian distribution that favors smaller numbers, where the likelihood of selecting a number is inversely related to its size raised to the power of 1.2. With 100 data points and 7 queries, we compare our model against binary search and a learning augmented TREEP. Our model slightly outperforms the TREEP, and both models significantly surpass binary search, requiring fewer than the logarithm of the number of data points in queries. This distinction emphasizes that while the Zipfian TREEP incorporates learning, it still relies on modifying existing structures. In contrast, our approach learns end-to-end, eliminating the need for human intervention, which is beneficial when we lack knowledge about suitable data structures. However, we note that learning augmented structures often provide guarantees that are harder to achieve with our method. Next, we examine a hard distribution to test if our model can learn optimal algorithms like binary search. In this case, we sample a dataset from the hard distribution and create queries by randomly selecting points from this dataset and adding noise. This distribution presents challenges due to its varied scales, so we use 15 data points and 3 queries. We find that our model successfully identifies a search method akin to binary search, and the error rates align closely with those of binary search. When we move to two-dimensional data, we find it less straightforward to represent points optimally since there is no clear way to sort in multiple dimensions. Our experiments show that different data and query distributions lead to different data structures, reinforcing the importance of learning both the structure and the querying method together. We set up a similar experiment as in one dimension, sampling coordinates independently from a uniform distribution. With 100 data points and 6 queries, we compare our model to a KD tree, which organizes points in k-dimensional space. Our model achieves about 75% accuracy compared to 52% for the KD tree, demonstrating its ability to leverage distributional information effectively. We also consider the hard distribution in 2 dimensions, where we find that the data structure our model learns resembles a KD tree, which is notable given the complexity of creating such a structure through recursive partitioning. In high-dimensional data scenarios, we face challenges due to the curse of dimensionality, which makes traditional algorithms less effective. We train our model on datasets sampled from a d-dimensional unit hypersphere, with queries designed to have a specific inner product with data points. For queries that match data points, traditional methods suffice, but for others, locality-sensitive hashing, LSH, becomes competitive. We train our model with a fixed inner product of 0.8 and compare it to an LSH baseline with 100 data points, 6 queries, and 30 dimensions. Our model performs comparably to the LSH baseline, and we find that it learns a solution similar to LSH by projecting onto 2 vectors in the 30-dimensional space. Section Summary. In this section, we explore various query distributions, including Zipfian and hard distributions, demonstrating that our end-to-end learning model can effectively discover optimal search algorithms and data structures, outperforming traditional methods like binary search and KD trees. We also highlight the model's adaptability to high-dimensional data, where it competes well with locality-sensitive hashing techniques, showcasing its ability to learn efficient representations and query strategies without human intervention. Section: Learning Useful Representations. In this section, we explore how to learn useful representations from high-dimensional data, which often contains low-dimensional structures that can enhance the efficiency of nearest neighbor searches. We investigate whether our end-to-end learning framework can effectively capture these structures. This task is complex because it requires us to optimize the learned representation, the data structure, and the query algorithm simultaneously. We focus on a specific task. Given a dataset of unique 3-digit handwritten number images and a query image, we aim to find the nearest neighbor in the dataset that represents the closest number to the query. We create these images by combining digits from the MNIST dataset. To build our nearest neighbor dataset, we randomly select 50 labels from the range of 0 to 199 and sample 1 training image for each label from the 3-digit MNIST. We also select a query label and its corresponding image, then identify its nearest neighbor in our dataset, which has the same label. Importantly, our model does not have label supervision. It only knows the nearest neighbor of the query. After training, we assess the model using a similar data generation process, but this time with images from the 3-digit MNIST test set. Both the data processing and query execution networks need to work with the same low-dimensional representation, so we train a CNN feature model as well. The setup remains unchanged, except now the networks operate on the features produced by this model. Since the distance metric we use is not Euclidean, we minimize cross-entropy loss instead of mean squared error. This approach only requires knowledge of the nearest neighbor and does not depend on the exact metric structure, making it applicable even when that structure is unknown. Ideally, our feature model should learn one-dimensional features that reflect the relative ordering of the numbers, while the data model organizes them, and the query model performs a search that takes advantage of the uniform data distribution to improve efficiency. Remarkably, all models learn to do this from scratch in an end-to-end manner without explicit supervision regarding which image corresponds to which number. We observe that the data model achieves 98% accuracy in sorting the features, and the query model finds the nearest neighbor with nearly 100% accuracy. Next, we evaluate our model's ability to utilize extra space for faster querying. In our experiments, we allow the data processing network to output additional pre-computed information alongside the rankings. We compare our model's nearest neighbor accuracy with a simple bucketing baseline, which divides the range into evenly sized segments and stores the nearest neighbor for each segment. Our model's accuracy improves consistently with the amount of extra space, indicating that it learns to compute useful statistics for more efficient querying. Finally, we highlight that our framework can address various data structure problems beyond nearest neighbor search. We demonstrate this broader applicability by applying our framework to the classic problem of frequency estimation, where a memory-constrained model tracks a stream of elements and estimates how often a specific element appears. We discuss additional data structure problems that our framework can tackle in the following sections. Section Summary. In this section, we explore our end-to-end learning framework's ability to learn representations that capture low-dimensional structures in high-dimensional data, specifically for nearest neighbor search using 3-digit handwritten number images. We demonstrate that our model can effectively utilize extra space for improved querying accuracy and discuss its broader applicability to other data structure problems, such as frequency estimation. Section: Frequency Estimation. In this section, we focus on frequency estimation. We have a sequence of elements and our goal is to estimate how often a specific element appears up to a certain point. We aim to reduce the average error between the actual count and our estimate. Similar to the nearest neighbor approach, we consider the size of our data structure and the number of lookups needed for queries. Our framework is adaptable to this problem, especially in streaming scenarios. We represent our data structure as a vector and utilize a multi-layer perceptron, MLP, as the data processing network to update this vector. When a new element comes in, the model updates several values in the data structure. Specifically, when an element arrives, the network generates several update position vectors and corresponding values. We then apply these updates to our data structure. Unlike the nearest neighbor setting, we limit the updates to a certain number of lookups because updates in streaming contexts happen frequently. For query processing, we also use MLP models to determine lookup positions. Additionally, we train another MLP that takes the values retrieved from these lookups and provides the final prediction. We evaluate our model using a Zipfian distribution, which is common in frequency estimation tasks where a few elements are much more frequent than others. The rank order of elements remains consistent across different instances, but the specific elements can vary. We use a data structure of size 32 and train our model with 1, 2, or 4 queries, with both data and query distributions following a Zipfian pattern. We assess the average error over streams of length 100 and compare our results with the count-min-sketch algorithm. Our model performs better with more queries, while count-min-sketch's performance declines as it is more efficient to use a single hash function rather than splitting memory into smaller parts. We analyze our learned algorithm and find it resembles count-min-sketch but with a crucial difference. Our model uses a smaller update value when new items arrive. This smaller update can be beneficial when the data structure is small and collisions are common. We believe this contributes to our model's improved performance. In another experiment, we fix the rank order of the Zipfian distribution while allowing the elements to vary. We simulate a scenario where certain items are more likely to appear, using 3-digit MNIST images instead of integers. We map integer streams to their corresponding MNIST labels and sample images accordingly. During evaluation, we use images from the test set. Since the distribution is skewed, smaller numbers are sampled more often. We employ a feature learning CNN to process these images before they are passed to our networks. We compare our model to count-min-sketch, which uses labels instead of images. Our model shows significantly lower error rates, demonstrating that by training on the data distribution, we can learn features of frequently occurring items and design an efficient frequency estimation structure. We find that our model allocates separate memory for these frequent items, reducing collisions. Section Summary. In this section, we describe our approach to frequency estimation, focusing on minimizing mean absolute error for a query element while adapting our framework for streaming settings. We demonstrate that our model outperforms the count-min sketch algorithm by effectively learning to manage updates and utilizing a smaller update delta, particularly in scenarios with fixed rank ordering of elements, such as when predicting frequently occurring items from a Zipf-ian distribution. Section: Other potential applications. In this section, we outline several other potential applications of our framework to support future research. First, we consider graph data structures. Many graph-related issues need efficient representations to handle connectivity or distance queries between vertices. For distance queries, one option is to use a large amount of space to store distances for all pairs of vertices, allowing for constant time queries. Alternatively, we could store just the graph itself, which might take up less space, and run a shortest path algorithm when needed. The challenge lies in finding a balance, using less space than the full quadratic representation while still answering distance queries more quickly than a complete shortest path calculation. Next, we address sparse matrices. Compressing sparse matrices can also be viewed as a data structure problem. For an m by n matrix, we could store the entire matrix for constant time access to its elements. However, depending on how many zeros are present and their distribution, we can design different data structures that use less space than the full matrix. There is a trade-off between how compact the representation is and the time it takes to access matrix elements for tasks like matrix vector multiplication. We also explore learning statistical models. Our framework can manage tasks like learning decision trees, where the input is a training dataset and the output is the model. During inference, the query algorithm would access parts of the model, such as traversing the decision tree nodes. This can help us investigate optimal algorithms and heuristics for learning decision trees, which are not yet fully understood. Additionally, we look at learning augmented algorithms. Recent studies show that traditional data structures and algorithms can be improved by learning about the underlying data distribution. For instance, learned index structures use machine learning models to enhance database indexing, leading to better performance for certain queries. By learning the cumulative distribution function, the model can more effectively locate records, improving query times compared to non-learned structures. Other approaches enhance data structures with predictions, like using learned frequency estimators to prioritize element storage in a tree. Our work is particularly relevant to research that trains neural networks for efficient nearest neighbor searches using locality-sensitive hashing, as well as learned hash functions. While these studies focus on enhancing data structure design with learning, we investigate whether we can discover data structures entirely through deep learning. Finally, we discuss neural algorithmic learners. There is considerable research on encoding algorithms within deep networks. For example, the neural Turing machine uses external memory to learn tasks like sorting. Graph neural networks have been employed to encode classical algorithms such as breadth-first search. These studies typically involve training deep networks with significant supervision to encode known algorithms, like using a sorted list to train a model for sorting. Some research has also focused on end-to-end learning of algorithms, such as using reinforcement learning to discover matrix multiplication methods or training neural networks to solve SAT problems. Our work contributes to this area by focusing on the end-to-end discovery of data structures.